Yeah, sadly Rob isn't here, so I kind of hoped he would join me and talk a little bit about how his experience was with this, with a Virginia driver. But yeah, so I'm here and will give this talk to you. And I was taking a look a little bit on how we could improve the situation with OpenCL generally and with the Gallium drivers inside Mesa, because currently the situation is kind of, we have like this Clover Gallium state tracker to do OpenCL within for Mesa drivers, but it kind of requires you to have a LLVM backend inside your driver, which is basically only true for the R600 or radeonsi driver. So nobody really can make use of the Clover state tracker. But we also have this kind of OpenCL C frontend inside Clang, so it's kind of a good idea to still depend on LLVM for all the parsing of the OpenCL C language, because especially with 2.2 or 2.1, Kronos actually released a specification for OpenCL C++, and I don't think that anybody of us actually wants to do all the parsing inside Mesa itself and translate it to whatever IR we support. So what we found was that there is this kind of upstream project from Kronos. It was in the past some fork of LLVM where they added support to translate LLVM to SPIR-V. So what some people started to work on is to try to extract those bits and make it a small LLVM module you could link against, so you don't have to link or use a LLVM fork, because that's something we wouldn't be able to do inside Mesa, because we kind of want to use the upstream LLVM. So yeah, we worked on this. So we have now this upstream Kronos project, which is called SPIR-V LLVM translator. It's just a small LLVM shared library you can link against and then use whatever upstream LLVM you have. So that would be nice to take OpenCL C code, push it through Clang, get the LLVM IR out, and just translate it to SPIR-V. So, and this is quite helpful, because in Mesa we already have like a SPIR-V to NIR layer for all the Vulkan drivers. So the kind of idea we came up to support OpenCL for our drivers is just, why not using NIR as the general purpose backend IR within Mesa for like all the different languages we might want to support even in the future. So we want to take whatever input we get, find a way to get it translated into NIR, and then driver only has to support NIR and basically get all the features and all the language support for all the languages we have inside Mesa. So the driver also, especially for OpenCL, it also has to support the compute shaders, which is kind of obvious. And there are some Clover functions a driver has to implement. And set compute resources is kind of the only one, but we kind of want to remove it because it doesn't do much anything besides calling or doing the same thing which we also have with set constant buffer and set shader images, what you need for compute shaders anyway. So basically, on the state tracker side or the Clover side, Gallium, all the driver has all the function support anyway if they support compute shaders. So the IR is really just the biggest problem right now. And if you look at what we kind of support right now, that's the not dotted line. So we have like our OpenCL files, we push it through Clang, LLVM IR, and then we kind of have the AMD GPU backend to support this for radeon-based drivers. But through OpenCL, we also are able to support SPIR-V files, and we kind of have to be able to translate between LLVM IR and SPIR-V, because we also have to link various shaders. So you could provide some SPIR-V files, and then you can provide some CL files, and you have to link them together. And so that's kind of where we want to go. And it would also allow us to actually support SPIR-V through Clover, because it's also required by the 2.1 specification. And it would allow us to basically, if your driver supports NIR, you basically get OpenCL for free. So, but there's still some stuff missing currently in the mesa tree, especially for NIR, like you have to support real pointers, and this is kind of painful because in OpenCL, the pointer is just some random value you can do basically everything with. So you can like add them together and have various other instructions working on them. So this is basically the main time we were spending on supporting this. Of course, we also need some additional instructions for all the different memory operations you are able to do in OpenCL and other random stuff like getting some workgroup IDs and workgroup dimensions and stuff like this. But that's just, that's pretty trivial. There's also the problem of OpenCL having like a really huge built-in library, so there are hundreds of built-ins you have to support inside your kernel, and then you need some kind of way to actually support it in NIR. Either you lower them to everything we currently have, or you try to add new opcodes to NIR to support those, which also kind of requires drivers to support new opcodes. So we kind of want to make this optional. Another big thing is that you also have vectors inside OpenCL of size 8 and 16, and in GLSL you basically only have like vectors of size 4. So there was also some work needed for this. I think there are still some patches left, but we also already did some basic work for this. So. And another big thing is OpenCL has quite a lot of rounding modes you can use to do some more explicit conversions between floating points or integers and stuff like that. So you can say, yeah, round the value to 0 or to positive, negative, stuff like this. So, and NIR doesn't support it at all. There are some FP16 rounding modes with SPIR-V, but the constant folding is broken with this, for example. So have to look into this, and the constant folding is really painful to get right because you don't have support for this in libc. There are some compiler extensions to do this, but some of them are kind of x86 specific, so it's kind of painful to get some generic code inside C without having any library support at all for this. Inside the Clover state tracker, there's actually just the support missing for SPIR-V files. Pierre was working on that, but and like the conversion from LLVM IR to SPIR-V. So for SPIR-V inside Clover, there's actually an OpenCL extension for earlier versions to accept SPIR-V instead of OpenCL C code. It's the IL program extension, which kind of got required with OpenCL 2.1, so it's basically the same work. There's this upstream SPIR-V tools project which you can use to actually parse SPIR-V files and link SPIR-V modules together, and so Pierre didn't really implement them themselves, so just use this project and it seems to work quite nice. So, but there's also like always a question, we could just convert all the LLVM IR also to SPIR-V just to make it easier for one driver, so they focus on one IR and then just working. So, yeah, and Pierre was basically doing all the work. I think it's still not upstreamed yet. I don't know if there's actually some missing features or some bugs in it, but I think it just lacks review. So let's talk a little bit more about this pointer support inside NIR. Inside GLSL, you don't really have pointers. You just have like references to some objects, and you always have like this kind of object as your base for all the offsetting you do later on, like kind of common in SSBOs and UBOs and stuff like this. So you don't have like a fixed hardware address or virtual address to work with. But with the, if you like enable this kernel capability inside SPIR-V, you get like real pointers, and you can just convert them to random SSA values and do whatever you want with them. So you basically get all the pointer arithmetic and pointer casting, dereferencing, and like basically everything you can do with pointers inside C. And what I was actually starting to wondering about is if you want to support bindless textures inside SPIR-V, you basically also need pointer support, because it's basically the same thing you can do in bindless textures. So you get your sampler object, and you can just convert it to a vec2 type and do whatever with it. I'm sure it's a bad idea to do this, but I mean, it's allowed by the specification, and maybe we should just fix the specification and disallow it. I don't know, but I think it's a problem we might run into it even on the graphics side anyway. So, but the problem with OpenCL here really is that if you have a pointer, it's not just a pointer, it's also a pointer to a specific address space. So you have like the global memory, which is like just a VRAM, and it can point to wherever inside the VRAM. You also have like the local memory, which is actually shared memory between all the threads inside the workgroup. And the workgroup is just a collection of threads sharing some resources, so you can share data between it. I think there's actually a name for this also for computers, but I don't remember yet. And there's also constant memory, which is a little bit special because you can't write to it for obvious reasons, but it's basically just a constant part of global memory. It's kind of like uniforms inside GLSL, like it has the same size constraints and stuff like this. So you can basically use constant memory basically like you use uniforms in graphic shaders as well. So you can have like your constant buffers or whatever and use that instead of plain global memory. Make it basically faster than global memory. And then, of course, you have also private memory, which is just visible to the current thread. And of course, SPIR-V wanted to be a little bit special here, so it also added this kind of function address space, which is kind of a weird thing, because it's mainly used if you pass like big data into a function through a parameter, and you have like this pointer to data, but in the end, it's just you would use it as some registers and don't really worry about this, but it's there and you kind of have to deal with it. And by default, or before OpenCL 2.0, you can't really cast pointers to different address spaces, but this kind of changed. So there's this problem with OpenCL 2.0, you got like generic pointers, and those are, well, the problem was that if you wanted to write some functions taking pointers as arguments, you would have to write one function implementation for each pointer type. So you had one for global, one for local, one for private function pointers, which were all doing the same thing basically. So with OpenCL 2.0, you got generic pointers, so you could just skip writing down the address space and just have an implicit cast to generic pointers. So in the end, you can just implement your function once and you are happy because you don't have to do stupid copies of the same code. So, but this also means that because you can't just take a generic pointer on your hardware and load the data from it, because you kind of have to keep track of what pointer type it is, because you have actually different instructions for each address space on hardware. So there are a few things you could do to actually support it. Like, you could just do a address space translation for each pointer, so you could basically map, for example, local memory to inside the global address space and stuff like this, but this might be not really efficient, because every time, I mean, it's basically on most hardware slower to access global memory than local or shared or whatever you have on your hardware. So Rob came up with the idea to basically just use fat pointers. So instead of having one scalar value for your pointer, you just turn it into a vector and have on one component the actual pointer value, and on the other component you have encoded the address space. And with this, you're able to, whenever you assign something to a generic pointer, you can just store the address space inside the second component, and at one time you can keep track of it, and basically with like some if-else code, you would be able to choose the right native instructions to use the pointer address in the correct way. So what we kind of do it with the NIR lower I/O lowering path. So yeah, basically works. And you could just do it like for all the pointers you have, even if you don't use generic pointers, and just have the other NIR passes clean up your code. So if you have constant folding, it would see, oh yeah, the second component's always this address space, so I can basically remove the entire if-else code again, and then have just the one load or store instruction for this pointer. But there's one problem, because it only really works if we also inline all the functions. And if we stop inlining, we kind of lose the information, because inside the functions we don't have the context of the value creation anymore, because we get like two components as the input and we don't really know what the actual type was. So we would be ending up with the if-else ladder anyway. But maybe we don't want to stop inlining stuff, so maybe that's not a big problem. If everything works out, the second component is optimized away, and you don't have much of a hassle. But you can have like kind of smart control flow where you assign either pointer with different address spaces to the same generic pointer, and then you still have this kind of code. So yeah, but maybe there are better solutions for this. I don't really, I mean, you could, for example, do address space translation only in those cases where you are not quite sure. So to support all the things, we kind of use the DREF things we worked on, I think, start of this year, where we basically we worked how we actually do the variable things inside NIR and kind of move to a more DREF kind of scheme. So what we basically do is that we kind of added a way to translate from SSA values to DREF and vice versa. So with the NIR DREF pointer as array, you can basically start a DREF chain from a fat pointer. So you have like the two components, you have this NIR intrinsics on that one, and then you start the DREF chain. And for this to work, we just assume that a simple pointer dereference is also the same as just basically assume it's an array and we index it at position 0. So it's basically the same thing, so we can do this. And for the other way, we have this NIR intrinsic address from DREF, so it's basically this the other way around. So we get a fat pointer back from a deref chain, so we get this vec2 type, and it avoids us to, well, it helps us because we don't have to deal with pointers in all the ALU instructions, because it's just a value, and well, the fat pointer is just an SSA value and not a pointer. So it kind of helps us because we don't really have to add new code for random instructions consuming this pointer value. But also because the deref instruction is actually opaque type, we don't have to fix up also the places where we actually use 32-bit vec1s, because in GLSL pointers are usually, or what we call pointers inside NIR are actually 32-bit types, but for OpenCL you can have either 32 bits or 64-bit, so it makes our life in this situation much easier. But there's also big problems with this approach, because you kind of have to decide if you have like this. Currently we have the GLSL type class to keep track of the actual type of the values we have. And we kind of have to decide, do we make it now a 128-bit type of value because it's a vec2, or do we stick with 64 bits, and then if we have a mismatch about the actual data inside the IR and what the actual type is, and then we have the actual data size. So you could also have like generic pointers inside global memory pointing to whatever. So at some point you actually have to store the fat pointer. So does it magically become vec2 type in a situation where we actually need it, or will it stay forever 164-bit value and we keep track of the type somewhere else? And then, of course, if we decide to store a generic pointer as a vec2 type, but all the other pointers as not as vec2 but vec1 stuff inside memory, then we have also this kind of mismatch about what the IR expect and what we actually do. So the biggest problem here is really, what do you do if you have like a struct having multiple generic pointers and you just store it inside some kind of memory? So also, what doesn't really help is that the specification is also not very clear about this, because it basically says that all the pointer types are not of equal size, and that's basically everything we get from the specification. The only well-defined thing is actually the size of global memory, pointers to global memory, because that's kind of the native pointer size of the device. So if you have a device doing 64-bit pointers natively, so that's the size of global memory pointers, but everything else is not defined. And because I was mainly working on this to support some SVM features inside Moreau, I was like testing a lot with this kind of SVM thing where you have a struct with pointers and kind of big pointer chains inside your input data. So you have to dereference a lot, and you have to read from pointers from memory and stuff like that. So this didn't really work out so well in practice, and I still have like tons of issues regarding that because of this mismatch of this actual size. And as I already mentioned, maybe if we just do address-based translation in a few situations, it would be a nice workaround to actually get it working in a proper way. Or maybe not. I didn't got to it yet. So. But let's also talk a little bit more about how to support all the stuff inside drivers, because that's mainly what I also want to focus on, because currently you have this kind of situation. If you want to support OpenCL inside your driver, you also need an LLVM backend, and I'm sure that most of you don't really want to do this. So we were starting to work on this, and because we are able to use just NIR for that, you basically don't really have to do many changes to your driver to actually support this. So you basically get a few of those specific NIR intrinsics, like load global and store global and stuff like this. So it's basically focused around memory and some OpenCL system values. Then it might be that we start adding new NIR ALO instructions to support some of the OpenCL build-ins, because lowering might result in worse code, and some of the hardware is actually able to support some of the build-ins in OpenCL, which we don't have in GLSL. So, but you don't really have to do this. And of course, you have to add some Clover-related Gallium functions, but maybe we remove that so you only add some caps, and that would be basically everything you would have to do to just support OpenCL inside your driver if you have a Gallium driver and support NIR. So I think that would be quite helpful for some drivers which don't really want to spend much time to support OpenCL, and if they basically get it for free, then it might be easier to just say, yeah, okay, we add support for those additional things, and if it's like one day of work, then it would be totally fine to do this. And especially for Moreau, because we don't have a NIR backend, or we don't support NIR, so for Moreau I had to actually write some NIR to NV, to our IR translation code, which is kind of done because I think it passes the same amount of piglet tests than our TGSI path, but there are some issues I want to address first before getting it really upstreamed. It still lacks some review, but currently Pierre is working on this, so there might be some, yeah, maybe I'm able to merge it at some point. Maybe this month or later, I don't know. So, state of the work. We still have like around 150 patches for all this kind of stuff. So it's basic, it includes all the SPIR-V work Pierre was doing, also the NIR patches for Moreau, but also some Freedreno and NIR patches to support all the missing features we need for OpenCL. Especially for NIR, for Moreau, the NIR path is actually slower than TGSI for mostly silly reasons. NIR has some certain patterns it produces which kind of make or increase our GPR usage inside Moreau. So it kind of tends to store constant values at the header of the shader program and a lot of other things. And because we don't do instruction scheduling inside our compiler inside Moreau, so we end up with a lot of live values and just doesn't work out that well. So I have some workarounds to get around this, but they are not nice, and they still give me a big benefit, and for some workloads I'm getting faster than the TGSI path, but it's still like, maybe a better solution, or maybe just implement instruction scheduling, I don't know yet. So, also the current pointer solution, it's a good idea, but it doesn't really work out that well in practice because there are tons of edge cases and there's tons of if-else code I would have to add in various places. So still have to think about what would be the best solution here. So maybe one of you have an idea. So, also, the current patches kind of breaks the graphics part, so we kind of have to fix this, obviously. So. And yeah, review on those other patches would also be welcome. Sometimes I post some patches, but it's mainly I wait for review of the Clover SPIR-V patches right now and the NIR patches for Moreau, and then kind of try to support or work on the other patches. So I was talking a little bit about constant folding, and this is like one of the constant folding code inside NIR. I was coming up to implement constant folding without depending on hardware-specific features. So I was just using pure C to implement this, and this is just the code for constant folding for a conversion from int to float types, rounding to 0. And it's basically using a lot of figuring out what is the max value of the type I've got, because we have like this Python code and we don't write one function for each combination of bit sizes, but it has to work for all bit sizes. So I have to figure out how big is the size of the source, and I have to do a lot of workarounding around undefined behavior inside C and stuff like this. And I was kind of surprised that I wasn't able to find one C library which would do all the magic for me. So I was kind of disappointed and was trying to figure out how much work it actually would be to support this for NIR and constant forwarding. It's quite a lot and it's kind of painful. And I kind of hope that somebody of you might know. Maybe there is some library I totally didn't see, and it might be actually better to just say, okay, no, we don't do it in pure C, and we always use hardware features for this. The situation on x86 is also a little bit weird, because you have like this, you can set the current running mode for floating point operations, but it's then set for the entire thread or CPU or whatever, and you have to revert it back, because then other code wouldn't work anymore, because it depends on this. There are also, I think, some SSE instructions to do this. I don't know how the situation is on ARM, actually. I just found that for some C implementation of OpenCL, there was also like this kind of code for ARM, because there is no real nice way to do it, especially in the OpenCL CTS. The ARM code was kind of like this. And yeah, I don't know. I don't want to have a bug in this, because debugging this is also super painful. So, but can we also use this work besides OpenCL? Because some might argue that OpenCL isn't the best API to do compute. So I was kind of thinking we could try to center around SPIR-V to be an IR to just state what kind of work has to be done on the accelerated device. So maybe we could actually have an OpenMP state tracker, which could be a nice alternative to OpenCL, and we just say, okay, whatever compiler there is, we have this kind of API for Gallium OpenMP, and say, yeah, you give us the SPIR-V and you give us the input data, and we do something with it on whatever device. So maybe it might be an interesting thing. And if you think about or keep HMM in mind, then a lot of copying data around would be basically for free from the driver perspective, because you don't really have to care about copies anymore. You just get the pointer of the data, and you just launch the SPIR-V program on your GPU and can just do accelerated stuff of whatever. Like, I kind of think it, or in most cases, I kind of assume that accelerating code with OpenMP is less painful than to do it with OpenCL, because I know that for some projects which were playing around with OpenCL, it didn't got faster at all, because all the launching a kernel overhead was just too big to be actually beneficial to use OpenCL. So, any questions?
So first of all, I'm sorry about constant folding. That's awful.
Yeah, I know. It's painful. It was actually the most painful code. Other combinations are much more simple, but it's basically the worst kind situation, yes.
So going back to your comment about if you have a Gallium driver that supports NIR, it's pretty easy to support OpenCL. Well, we have a Gallium driver now, and it supports NIR. I don't think we have compute shaders hooked up yet, but once we do, it would be very interesting to try and run this stuff through that stack as well, and just sort of see what things look like. I'm interested in it not so much to support OpenCL, because we already have too many OpenCL drivers, but because with Vulkan Compute taking over more and more use cases. It'd be interesting to see sort of where we can, like, what features from OpenCL we think would be useful to try and pull into the Vulkan world, and from our perspective, what would be easier to hook up in our compiler. So it's not really a question, it's more of a comment. But so yeah, it'd be cool to hook it up and see where things are at.
There's this tool, I think some guys from Google and maybe from CodePlay did to translate OpenCL SPIR-V kernels into Vulkan compute kernels. So why didn't you just use that? Or did you look at it to look up the translation rules or something? Because for me it looks like you just did the same, translating from the OpenCL SPIR-V to and lower it to compute kernels, and and extending it, of course.
Yeah, well, the main reason I was working on it was to support or basically have an HMM user space for Nouveau. So that was the main idea. So, or the main reason. Because we don't support Vulkan in Nouveau, back at the time I was thinking, yeah, maybe doing this is less work than coming up with a completely new Vulkan driver and improving also the translation from OpenCL to Vulkan as well. So, and I mean, also Vulkan doesn't really support all the SVM features we have in OpenCL, because with the fine-grained system SVM level, you can basically malloc memory, pass it into the kernel, and access it from your GPU without having to copy any data. So, and I mean, I don't really see that this work Google is doing will be able to be a full conformant OpenCL implementation anyway. So maybe they will, I don't know, maybe they will get to it, but I was kind of thinking, yeah, it wouldn't be that great. And maybe it would be too much work to actually do this work.
Yeah, it doesn't. It's a subset, of course.
Yeah, I know. But maybe they want to add more features, and maybe they get to it. I don't know. Or maybe they don't care. So.
Other question? Okay, this is all. Thank you, Karol.